Okay, this video is on dissociation equations, how to write them, what they are, how to write them, and later we'll go into how to calculate or using calculations in solution chemistry or using working with molarity. Okay, so first of all, how do we get aqueous compounds? They're when soluble ionic compounds dissolve in water. The proper term we say is that they dissociate into ions. So on the next slide, I have a picture. I'll show a picture of four water molecules surrounding an ionic compound, sodium chloride. The things to notice on the slide, on the following slide, are when you'll notice that water. So this is a background on water's shape. So oxygen's a central atom. It's in 6A. So we draw a bent shape like this. Oxygen has a 3.5, hydrogen has a 2.1 electronegativity, and so you get dipole arrows that go like this. So you get dipole arrows that go like this and like this. And water is or oxygen is negative, and the hydrogens are both partially positive. So this plays an important role when we write the term AQ in a balanced reaction, we write the term aqueous or the physical state AQ. So what does this mean? So and then the term dissociate. So here's a hopefully a picture. So this is the picture I took was sodium iodide, but it does the same thing. So we have a metal and non-metal. So we have an ionic compound which is known to be soluble. Iodides are soluble. And so, what does this mean? What does the term AQ mean? Well, you have two. So there's, and when we get into the first law of thermodynamics and heat chemistry, there's actually more detail that happens than just what we're going over in this tutorial. However, this should serve as a good overview. So there's three things that need to happen actually, and we cover this more in detail, like I said later. There's three things that need to happen. The ionic compound needs to split. Okay, and it does. So the force that holds these ions together, the electrostatic force, breaks apart. The next thing that needs to happen is actually the solvent. So this is our solute, is the NaCl. So this needs to detach. Okay, and the next thing that needs to happen is water needs to detach. So these hydrogen bonds need to break as well. Okay, and so you'll see that, let's go back. So this water molecule detaches, and we see that the negative part of water will face towards the positive ion, the positive cation. Okay, and so again, another solvent water molecule breaks away from its hydrogen bond. Basically, this positive is competing with, if we rewind this is a partial negative and this is a partial positive, and this positive is a lot stronger than this positive. So this is a full-blown cation, and it's competing with the hydrogen bond here, and it ends up winning that little battle. And so water will go towards the sodium like that. Okay, and then another water will go like that. Okay, and then sodium, the sodium ion gets completely surrounded by negatively charged, partially negative oxygens. Okay, and this picture is really important. Okay, to note that the negatively charged oxygen, the partial negative, is facing the positive cation. And so you might guess the opposite happens on the anion, which is exactly what occurs. The partial positive hydrogens will surround the negative anion. Okay, and then so water breaks apart from its solvent hydrogen bonds, and it surrounds the anion like that. Okay, and that's when you write AQ, that's what you mean if you write AQ in a balanced reaction, or like, if you are doing a math problem. And many times you'll see that this concept, the concept, it actually is, your understanding of the concept will lead you to like the correct steps that you do mathematically. So the two always go hand in hand. In fact, actually, the concept always happens first, and then there's a result, is you're able to do like perform some math calculations based on some rule or some law, but it's always, always, always the concept first. Okay, so with that said, we'll head into molarity calculations and how you do them. Oh, I'm sorry. So first we're going to go into writing dissociation. So we want to write, we don't want to draw a picture every time. So we want to basically write a balanced reaction for dissociation. Okay, and the way you do that is just go basically going from formula to ion. So we just write these split up. So the way this works is every time one of these dissolves, a zinc nitrate ionic compound. So let's say this is a solid zinc nitrate. If you add it to water, it's going to do this. It's going to go zinc 2 plus. Actually, there's actually an error here. This should be a 2. Zinc always makes a 2. And so, and we would write AQ plus nitrate NO3 minus 1. Okay, and to take care of this 2, you actually have to balance these. So dissociation equations, they make sure they're balanced. Make sure these guys are balanced. Okay, so that 2 means we should put a 2 there. So for every one time that this dissolves, this is going to be important for when we do molarity calculations. Every time one of these dissolves, it's supposed to be a 1. Every time one of these dissolves, it will create 1 zinc and 2 nitrates. So every time one of these dissolves, you end up getting a total of 3 particles. So we need to observe the correct ratios here. So here we have perchloric acid, a strong acid. Every time one of these dissolves, you will get one of these, 1 proton and 1 perchlorate ion. Okay, and we should write AQ after. So the balanced relationship is every time one of these dissolves, you generate 1 proton and 1 perchlorate ion. Okay, silver acetate. Little side note here, acetate, if you further condense this ion, you get, if you combine the carbon, C2H3O2. So sometimes acetate may be written like this, okay, which is what's happening here. So there's 1 acetate ion and 1 silver. So the ions are Ag plus 1. Ag always only makes a plus 1 anyway, and acetate. Okay, and then we go ahead and balance it. It's already balanced, so 1 and 1. Okay, potassium sulfate would be a K plus and SO4 2 minus, right, AQ. Okay, and there's 2 potassiums in the formula, so every time one of these dissolves, you'll get 2 potassium ions. So the ratios are 1 to 2 to 1. Okay, and then HBr, hydrobromic acid, we have H plus, aqueous, and Br minus, aqueous. Okay, so that's dissociation. Split it into ions. It's similar to just when we were naming compounds and we wanted to like write the ions out. It's a big reason why we spent a lot of time on ionic naming is so we could actually do these and get the correct charges. Okay, so let's go into how you express concentration. Okay. Oh, I'm sorry. One side note on vocabulary. So hydration is actually this process. So if we go back to this slide here, in this animated slide, this process is called solvation. When the solvent, water, surrounds the solute, that process is called solvation. If water is the solvent, which is a lot of times the case, it's called hydration. That process of that happening there. Okay, so let's go to this slide here. I'll go over some vocabulary terms. So these are basically what was on that slide, but just in words here. Okay, solute is the substance that gets dissolved. So in the case of the previous example, it was a sodium chloride. and the solvent is the substance that does the dissolving. Okay, if you have so if you have two, you could have two liquids. You could have a liquid solute and a liquid solvent. If that were the case, it would be the I'll just write a note here. If you have two liquids, the one in greater concentration would be classified as the solvent. You could also have a gas mixture where you have solute and solvent. So, like Earth's atmosphere is one big giant mixture, so it's just one big solution. You could also have alloys. So, if you play an instrument like brass, is actually a solution. So the two metals are dissolved together. But in chemistry, most of the time we'll be working with some ionic compound that is dissolved in a, or an acid or base that's dissolved in a solvent, and most of the time that solvent is water. Okay, so molarity is how we measure, the most common way to measure concentration. So it's moles of solute. So I should actually be more specific here. Moles of solute divided by liters of total solution. Okay, so that's molarity, and we represent it with a capital M. Okay, so let's go into right into a problem here. So we want to write the concentration if 10 grams of cane sugars dissolve in 200 milliliters of solution. So this question says, what is the molarity of sucrose molecules in this solution? So here's the way we do this in AP chemistry. So you might notice there's an equation. Okay, and I convert to moles and I change this to liters. So one side note here, this your volume here. If you wanted to abbreviate this, you could get M, capital M equals N over V, and this must be in liters. A lot of times you'll find it in milliliters, which is a one-step conversion. Okay, so you'll see that there's an equation. However, I highly recommend I do my examples like this. My students, for the most part, go this route as well. I highly recommend just doing this with units. Okay, and because you're keeping your skills consistent, and this is transferable to all kinds of different problem solving, like using the heat equation, using something called Raoult's law, is lining up your units. So let's just do this by units. Here I have the molar mass, and what I want is my final answer is I want it to say moles over liter. I want my units to say that. Right now I have grams and milliliter, and I want it to say this, moles over liter. So I'm going to start by making the numerator say moles. So I'll change this, and we're going to do this problem all in one line instead of doing like some plug and chug style. So we'll go, so I'm going to inverse the molar mass to get moles on top. 1 mole, 342 grams. Okay, and right now I'm good on the top. So right now that works. So now my goal is to make it say liters on the bottom. So I need to divide by liters. So what I'm going to do is I'm going to inverse um, the volume, and I'm going to put 1 over. Now the milli to liter. So if you use the metric system mnemonic, King Henry died by drinking chocolate milk. This is our most common conversion. You forget about deca, hecto. Sometimes we might use kilo, not often. This is the number one to remember is base to milli and milli to base. It's always 3. 1, 2, 3 this way, or 1, 2, 3 this way. Excuse me. So What I like to do is I don't even bother with any of this stuff. What I do is if I see milli, I do this. I go 200, and I just do this times 10 to the negative third L. Okay, and notice that I don't bother moving this decimal, and what it does is I get very little, if any, sig fig mistakes. Okay, so if you start moving this decimal point around, you might lose a sig fig here and there. So what I do is I just write exactly what they give me in the problem, and I just about never make sig fig mistakes this way. Okay, so here's my setup, and now I have moles, and now I have liter in the denominator, so now it matches what I was going for in the beginning. Okay, so I use my um, so get my calculator. Okay, and then I enter it like this. So I go 10, and then I hit divide, and then I like to put the entire bottom part right here and here in parentheses. So I go 342 times 200. And I enter exponents this way. I use this E button, and you should too. It's a lot faster. So I go second, and then I hit that E button, and then I hit negative 3. Okay, and then close parentheses, and then I hit enter, and that's my answer. So I should have this number here has 3 sig figs, and this has 3 sig figs. I really should include a couple more decimals in my molar mass, but I'll just leave it as that. So my final answer should be 3 sig figs. So it should be 0.146. 146 moles per liter, or capital M. Okay, so that's a basic molarity problem. Okay, so usually you do molarity before you're going to make a solution. So here are the steps on how to make a solution. So you would weigh the desired amount for a given concentration. So let's say you want a 1 molar sample of sodium hydroxide, and let's say you want 1 liter of it. Okay, so there's a problem to work out here. You'd have to calculate the grams. Okay, so let's say you run that calculation and you get the grams. You weigh that amount, you put it in a volumetric flask. So this is a volumetric flask. And you add water. You use a wash bottle, okay, to rinse off the sides. Like say some of the solid gets stuck on the sides. You would use a wash bottle and rinse off the sides. Then you add water. Okay, up to, you could go higher than what's pictured here. You could go like this high. Okay, and you'll see a line. This marker represents 1 liter. Okay, so you would you stop right here, because if you add water, it's going to go up really fast, the volume. Okay, and then you use your wash bottle, and then you slowly fill it up to the line here. Okay, and then you would actually take this flask and invert, so you would turn it upside down and then back the other way, and then back this way. And you're supposed to do, I believe it's like, there's actually a number. I think it's like 20 inversions to mix the solution. Okay, the reason you have to use a volumetric flask is because this actually adds to the total volume. And you know this because intuitively, because when you add ice to, like, say you want to it's hot outside and you want a cold water, ice water, so you fill the water up with liquid water, and then you add ice, you'll notice the volume increases. So when you add solids, it actually adds to the overall volume. And remember this molarity here, it has to be it's the volume in that equation is the volume of the whole solution. So it's solute plus solvent. So this is the correct way. You have to use a volumetric flask. You cannot make this in a beaker. So you can't just like pour this, you can't do this. So you use a beaker, put your solid, and then measure out 1 liter. If you measured out one, if you did it that way, you would actually have more than 1 liter because of the solid at the bottom. Okay, so it has to be done in a volumetric flask. Important point, okay, for when we start seeing lab-based AP questions. Okay, so here's a question that says describe how to prepare stock solution. So this is a real common molarity problem, is like a real practical one that you may use in labs. So we need to know how much of this to weigh to get it this strong, this concentration, and we require 200 milliliters of it. Generally, you wouldn't make 200. Usually, you would make like 1 liter because that's the size of the volumetric flask. Okay, so these would be the steps. I always like to expand this and put it in moles per liter, and then that allows me to do unit analysis to solve this problem. So instead of writing capital M, capital M is pretty useless. You should always try to expand the unit to this. Okay. So I basically my goal here is I want all this stuff right here, moles per liter and ml, which is as good as L. I want this to say grams. Okay, so I need to get rid of this and make it all say grams. So first thing to do is get rid of the denominator, okay, because we don't see denominator here where it says grams. So I need to multiply these together. So I go 200 times 10 to the negative third liters, so the liter cancels. And now I have moles of NaCl, and I need grams. Okay, so I go like this. I have the molar mass. So I did that beforehand. Okay, and this is how I get the mole of NaCl to cancel here. Okay, and I multiply these numbers together, and my result should have 2 sig figs because of this number, so I get 3.5 grams of NaCl. So this question says describe how to prepare. So you would weigh 3.5 grams of NaCl. Next, you would add to a volumetric flask. Next, you would wash the sides. Just the same steps as I showed on the previous slide. Wash the sides of the volumetric flask with a wash bottle. And next, you would use, if one exists, I don't think one even exists, but we would use a 200 milliliter volumetric flask. Add to a, I should actually add this here, 200 ml volumetric flask. Okay, now you add water up to the mark. Okay, generally you would stop right before the mark and then use the wash bottle so you could go slowly and get it accurate to the mark. Okay, so that's how that would be done. Okay, dilutions. This is another type of problem that is that's related here. So let's say you have a stock solution that's 0.01155 molar hydrochloric acid, and we want to dilute it to this concentration, and we require 100 milliliters of it at this concentration. So there's an equation for doing dilutions. Here's the equation. It's M1 times V1 equals M2 times V2, and the M1 here represents the starting, this is the stock solution, or the concentrated one. Okay, the starting one that you're starting with. Okay, the M2V2, the twos here are the diluted amounts. In other words, in terms of this problem here, you're given M2 and this is V2 because these are the diluted amounts that you want to dilute it to. And the other, so basically there's four variables here, M1, V1, M2, V2. You're given M2, V2, and out of the stock starting one, you're given M1. So let's try to color code this. This is M1 here. Okay, and so basically you're solving for V1. Okay, but it's not as simple as that. Let me show you what what you're actually solving for in V1. V1 represents the amount of stock to use, so it doesn't describe how much water to use. For that, you're going to have to um, for that you're going to have to subtract. So I'll show you what I mean. So you would do so to solve for V1, the volume. So we're solving for the volume of this we need to make it this dilute or this, yeah. Okay, so this would be M2 V2 if I solve for V1 here over M1. Okay, if I plug my numbers in to the negative fourth times 100, leaving this in milliliters, so that means my answer is going to be in milliliters, which is okay. I mean, I could convert, but I know I'm going to get this really tiny number, so I'm just going to leave it in milliliters. M1 is 0.0155 capital M. So that M cancels, so my answer will be in ml. And I should have three sig figs, 3.37 milliliters. And what is this number? This number is how much concentrated HCl to use. So what I do is I measure out. You use what's called a pipette. Okay, and a lot of times it has a bulb or like some type of like a drawing up mechanism. Okay, and you would measure out, this is our concentrated amount. So this is the 0.0155. And you draw up 3.37 milliliters of this. Okay, next, how much water do we need is actually, so our total final volume is 100. So water to use is always V2 minus V1. That's how much water to use. So which would be 100 minus 3.37. I'm subtracting here, so I need to apply the add subtract decimal point rule. This has no decimal points. This has two. Our answer should be 0 decimal points, so 97 ml water. Okay, so you take this and I suppose a flask would work. So you can use a flask. Okay, and then you add the 97 milliliters of water. Okay, and then the next thing, so here's 1, 2, and then step 3. The reason you do this is you always add acid to water. And it goes add acid to water like a good student oughta. I don't even know how to oughta. Okay. And there's a mnemonic because there's a safety issue here. If you do it the other way around, water to acid, it might release a lot of heat. So you want the water there to absorb all the heat released by the mixing of the acid in the water. So that's why you add the water first. Okay, then draw up I should actually number these differently. So this should be step 2, this should be step 1. Okay, and then step 3 is you add the 3.37 and then you mix. Okay, so that's a dilution problem. Okay, next is a number of ions in solution, this problem. And I believe I'm going to stop here and I'll do this as a separate tutorial.